Hello class 12th. In this lecture, in the last lecture we have discussed about the Huygens principle and the law of reflection. We have derived that equation. In this lecture we will discuss about the law of refraction using the same Huygens principle and the optical path and the effect of wavelength, means the change in wavelength while traveling from one medium to another. I have tried my best to show you by animation how the light means the wavefront is coming from the first medium and going to the next second medium. So just see, then after that in the sheets. Let's start.
For that, let us consider one intervening medium, second medium, SS dash. A wavefront AB is falling towards the second medium. See here. Let's draw a perpendicular line on this wavefront will give the direction of ray. By the time this first point is touching the second medium, the above line, above ray will start proceeding and the secondary wavelet will be formed this way. So this is the time when the upper ray comes toward the second medium and the first line, first ray start producing the secondary wavelets, and the common tangent to all produced is called refracted wavefront. Same way for the other rays in the wavefront will be seen like this. Same way for all the points between A and A dash will act as a new source of secondary wavelets. So they will produce in the form of circles because they are point source right now. And if that tangent is common to all, so this will be the A dash B dash will be refracted wavefront.
So see here, the refraction of plane wave at plane surface means derivation of Snell's law using Huygens principle. So let's draw the intervening interface to media. So let us consider this SS dash is the interface of, means the boundary line of the different medium. So I'm supposing that this is medium 1 and this one is having medium 2. In the last derivation there was a reflection. This was a reflecting surface. Here this is the different medium. We can consider this medium is denser, so the light is coming, means wavefront is coming from rarer medium towards the denser medium. So let's draw first the incident wavefront. So let this AB is the incident wavefront, and what we know that perpendicular drawn on the wavefront gives the direction of incident ray. So let's draw the two extreme incident rays. So here I have drawn the two incident rays, the perpendicular on the wavefront, and let's draw the normal to calculate the angle of incidence. So here this is the angle of incidence. So now what will happen? By the time this ray will reach up to this end, this ray will proceed in this medium. So but this will be refracted, means this would be original path. So this will be reflect toward the normal. So first I am drawing the original path. What would be the original path if we are considering there is no media, there is no different medium. So this will proceed in this way. Let's draw that. So this ray is proceeding up to here. By the time this ray is proceeding here, this ray, if suppose there is no medium, so this will go up to here. So by the time it is coming here, this would proceed up to here. But since there is a medium and that is a denser medium, so this ray will bend toward the normal. Let's draw that. So this will be refracted wavefront, refracted ray. Now we have to find what? This is the incident wavefront. We have to find refracted wavefront. What we will do? The distance traveled in time t here and distance traveled in time t here. So we will take an arc. We will take an arc here and we will join the arc with that. So that will be refracted wavefront. So we have to prove that this will be common tangent for all the refracted wavefront. For that, first of all, let us consider in this medium, let the velocity of the light be v1, and in this medium let the velocity of the light be v2. Here we know that v2 will be less than v1. Why? This is denser medium. And let from B to this point, say this is A dash. From B to A dash, the light took t second. So the distance traveled from B to A means BA dash will be V1 into t. BA dash is equal to V1 into t, because this distance is equal to velocity into time. In this medium, velocity is V1 and time t. So BA dash is equal to V into t. This is the distance. So as we have supposed, in the first case, suppose there is no medium. So this wavefront would have been proceed up to here. I'm drawing that, and let this point be D. अगर ये medium ना होता, if suppose there was no such medium like this, there was same medium 1 and medium 1, so this wavefront AB would have proceed to this point, and the wavefront would have been would be A dash D. So this would be the wavefront, but there is a medium. So what we can say, the distance traveled from B to A dash is equal to A into AD also. So BA dash is equal to V1T and also equal to AD. And now see, by the time when B was approaching here, in the same time this point source would have been producing what? The secondary wavelets. Suppose this is increasing and increasing and increasing to here. By the time it is approaching here, this wavefront, secondary wavelet, comes up to here. For this point, this will be also increasing there, but this will produce a little bit smaller, because it will take time to come here, then it will produce the secondary wavelets. Same for this point, the ray will come here, then it will produce secondary wavelets. So if we draw the common tangent on all these secondary wavelets, and if this tangent is common to all, then this will be called refracted wavefront. So I'm taking an arc in this medium, the velocity is v2, in time t, distance is equal to v2t. Suppose I'm taking an arc somewhere here, and that will be equal to v2t. How? Just I'm drawing draw. So as I said, there will be many secondary wavelets. So I'm taking an arc, and suppose somewhere here, and naming this as B dash, in such a way that the time taken by the light to come from here to here is the same time taken by the light after refraction to come from here to here. So if this is the second medium, so we can say AB dash, see here, AB dash is equal to V2T in the second medium. So now taking this as equation 1 and this as equation 2, so dividing second equation by equation 1 means AB dash upon A dash B, this B A dash, I'm writing A dash B, is equal to V2T upon V1T. T will be cancelled. What you will get? V2 upon V1 is equal to AB dash upon A dash B. And this AB dash, A dash B, this one, A dash B, where is that? A dash, this one, A dash B is equal to V1T. A dash B is also equal to AD. So instead of this, we can also write AB dash upon AD. What is AB dash? AB dash is the arc, the radius in the second medium, and AD is also an arc when the medium 2 was absent. So I am writing here. So V2 upon V1 is equal to radius in medium 2, you can see here AB dash, and radius if medium 2 was absent, means AD, means AB dash radius in medium 2 में radius, and radius if medium 2 were absent, मतलब जब medium 2 ना होता तब की radius. चूँकि this is AD, we are considering that this is in medium 2 when the medium 2 was absent. So here दूसरे मीडियम में रेडियस अपॉन दूसरा मीडियम अगर ना होता तब की रेडियस. दिस इज V2 अपॉन V1. दिस इज सपोज इक्वेशन 3. नाउ देयर आर मेनी rays on this wavefront. We know that we can draw. I'm going to draw one more ray. If we anyhow is able to prove, if we anyhow can able to prove that this wavefront is common to all secondary starting from this. So this will be refracted wavefront. What we are going to listen carefully. अगर हम ये साबित कर दें कि यहाँ से जितनी भी रे चली है दूसरे मीडियम में, अगर ये टेंजेंट हम ड्रॉ करेंगे और वो टेंजेंट सारी रिफ्रैक्टेड वेवफ्रंट पे कॉमन है, ये जो टेंजेंट हम ड्रॉ करेंगे, आई एम ड्राइंग फर्स्ट. सो दिस इज आवर कंसीडर्ड रिफ्रैक्टेड वेवफ्रंट. सो we will take one more ray anywhere between this, because this is consist of infinite number of rays. So we will take any ray, we will proceed up to here and it will bend toward this way, toward the normal. अगर ये जो बेंड हुई रे होगी उसका भी टेंजेंट यही निकले, means this will be common tangent of all, as I have drawn all the circles. If this we can prove, so this will be what? That A dash B dash will be our refracted wavefront. For that I am taking one more ray here, say third ray, any ray we can consider. This point to be suppose M, and I am proceeding it further. And suppose this point is Q when the medium 2 are absent, but since there is second medium, so it will be refracted this way. So let this is the refracted ray, M dash point. So we have to what prove? This is the common tangent, because one arc will be also will be there for all the secondary wavelets will be originating from here. So that circle will increase its radius. So this radius is for this here, for this one, and this radius for this one also. So what we will see, wait here, this will look like this. This point producing secondary wavelets, this point producing secondary wavelet, and this is just arrived here. So you can see here this is the common tangent for all. So we have to just prove that this is the common tangent for this one. We can say that okay, this will be common tangent for all, and this is what? Secondary reflected wavefront. So let's do that. So now we will take this point as point P and take two triangles, P A dash M dash, P A dash M dash, this is small triangle, and second A dash B dash, the bigger triangle. You can see in this bigger triangle and in this small triangle, this angle is common and this is perpendicular rays. So we can say that this small triangle P A dash M dash and the bigger triangle A dash B dash are similar. Using similar angle property, similar triangle property, the ratio of two sides will be same corresponding sides. So let's draw that. So I have written here these two triangles. So I am taking P A dash upon A dash, small one side and the longer side, P A dash upon A dash, and second side P M dash upon A B dash, P M dash upon A B dash, taking this as equation 4. Now again, and another one, P A dash Q A dash D. P A dash Q means we are considering that there is no medium, and A dash D, the dotted line wala smaller triangle and the bigger triangle, P A dash Q and A dash D. Same way we will take again P A dash upon A dash, because this side is common, so writing here, and P Q upon A D, जैसा कि हमने इसमें लिया था, same way here also P Q upon A D. So making this as equation 5. Now I'll compare 4 and 5. The left hand side is same, so right hand side will also be same. Say that I'm writing that PM dash upon AB dash is equal to PQ upon AD. Now on transposing this PQ on this side, let's see what will happen. So PM dash upon PQ is coming here and AB dash going there. PM dash upon PQ is equal to AB dash upon AD. You see here AB dash upon AD. This is what all about this ray. Now we are talking about this, so it is coming for this also. So what we will write here? So what we have obtained, see here, PM dash upon PQ is equal to AB dash upon AD. What is AB dash? Radius in medium 2, And what is AD? Radius in medium 2 if medium 2 were absent. Means this PM dash upon PQ, see here, PM dash upon PQ, and here it was AB dash upon AD. This is coming for both the rays, means for this ray and this ray. Means same way we can consider any ray from A to B and we will get the same radius. Means what? This proves this is the common ray tangent for all these secondary wavelets. So what we will say? We will say hence A dash B dash, A dash B dash means this one, A dash B dash, is a common tangent for all secondary, this is missing, for all secondary wavelets originating from A dash. Originating from A dash means whatever the secondary wavelet starting from this is what? The common tangent for all. This means, this proves that therefore A dash B dash is refracted wavefront. This one, this is the common tangent for all. Now we have to what prove? The law of reflection. So here you can say this is the angle of incidence, this plus this is angle 90, same way this plus this is also angle 90. This is the common angle, so this angle will be angle I. And suppose this is the distance up to which by the time this is coming here, this ray is coming here, so I have proceeded little bit longer, so producing this is a little bit longer here also, just to show the angle of refraction. So for that let's draw normal here. So this angle will be what? The angle of refraction. Same way here, and this will be the angle of refraction. See here, this is the refracted ray, this is the normal. So I'm saying that this is the angle of refraction, and this plus this, see here, this plus, sorry, this one, only this one. So this is the refracted wavefront. This plus this will be what? 90. Same way, this is tangent for this, and R plus this one, the remaining one, R, sorry, don't say this R, this one plus this one is also 90, and this complete angle is common. So this is what? This is common angle. See here, this plus this is 90. Same way, this plus this is also 90. This is the common angle, so this will be R. So what I will calculate? I will calculate sine I and sine R. So let's see. So let's calculate first sine I. See here, this is the angle I. The perpendicular upon hypotenuse means BA dash upon AA dash. See here, and now sine R in this triangle, this perpendicular and this is hypotenuse, AB dash upon AA dash, this one. Now let's sine I by sine R. So here sine I by sine R, BA dash upon AA dash divided by AB dash upon A dash will be cancelled, but we have got BA dash upon AB dash. So see here, what is BA dash? BA dash is V1t and AB dash is V2t. Let's fill the value. After filling the value, t will be cancelled. So we got sine I by sine R is equal to V1 upon V2, and we know that for the two different media, the ratio of velocities is a constant quantity, and this is what? The refractive index. We have proved this medium 1 to medium 2. Sine I by sine R. This is proved, this Snell's law. And second thing also, incident wavefront, refracted wavefront, normal, or you can say incident ray, refracted ray and normal all lie in the page. Everything is in the page. So this proves the law of refraction also. Our next topic is optical path. First of all, let's see the diagram. Consider this is any denser medium of refractive index small n, the incident ray, the normal, the refracted ray, naming this A, O, and suppose this point is B. The distance traveled in the second medium is OB. Let OB is equal to, I'm just giving some symbol, BD, and the refractive index of the medium is N. So optical path is defined as the product of refractive index and the distance traveled by light in this medium. This product is known as optical path. So as I said, the product of refractive index of the medium and the distance traveled in the medium, denser medium, is what? Optical path. Let this medium be air. So here the velocity of light will be with c, speed of light, and this medium be any medium whose refractive index is n, and here the velocity of light is being v. So the time taken to travel this distance, time is equal to distance upon velocity. So distance is capital D, we have taken OB as a D, and velocity is v. So the time taken by the light to cover this distance from here to here is this much, or we also know that small n refractive index is equal to c upon v. Filling the value of v is equal to c by n. From here let's put that. So t is equal to d upon, instead of v what we can write? c slash n. N will go up, so n into d upon small c. And now let the distance travel in the same time by this ray, means in air. Let's calculate the distance traveled by light in air. Distance traveled by light in air in same time t. So in air I am considering it with the small d symbol, in medium capital D, in air small d. So small d is equal to what? Speed of light in air into the time. So small c, what is the time taken? N into d by small c, n into d by small c. Small c cancelled, so small d is equal to n into capital D. So the distance traveled in air by light is what? Optical path, and the product of the refractive index and the distance traveled in the medium is what? The optical path. Both we can define. What? Again listen, distance traveled by light in air in the same time, the product of refractive index and the distance traveled by light in medium in the same time. Okay, so this is what? Optical path. So the next topic is effect of wavelength. So we know that the refractive index is equal to velocity of light in air upon velocity of light in any medium, and velocity is equal to frequency into wavelength. Frequency into wavelength in air upon frequency into wavelength in medium, any medium. You can take any medium. So we know that the frequency, while changing the medium, frequency never changes. So frequency will be cancelled. What you will see here, wavelength in air upon wavelength in medium. So this is what? Refractive index. Or you can calculate the wavelength of light in any medium by knowing the wavelength of light in air and the refractive index of the medium, by which we can calculate the wavelength of light in any medium by knowing the refractive index of the medium and the wavelength of light in air. That's it.
Here I'm ending this lecture, ending this session. In the next lecture we will start the new chapter, interference of light, because you are not putting any query or any doubt or any numerical problem. So in the next lecture we will start our new chapter. Till then, be safe, take care, and thank you.